Good afternoon, everyone. Welcome to week fifth of the live sessions on the course Finite Element Method. I'm your TA Danish Bashir from Structural Engineering Division, Department of Civil Engineering, IIT Madras. In last class, I told you about the basic steps that we follow in the finite element method or the finite element analysis, how we discretize our problem into small domains where we saw only 1D domain where the problem was 1D also. And I also tried to solve one boundary value problem with a different number of elements, wherein I started with for one element, then two element, and three elements, and then I showed you how the solution accuracy improves with the help of using more number of elements. And in each element, we assumed, I think, linear trial solution, and obtained that solution for one element, then two elements, and three elements. And then continuing on the same thing, today we will be studying about the first important topic in this finite element analysis is that the axial deformation of the bar, or what we call as commonly as we will be studying about the bar elements, how we carry the finite element analysis of a bar which is subjected to uniform axial tension, or it can be compression also. There is only the difference between signs. So let us start with that thing. So today's topic is axial deformation of bar. So let's consider a bar which is fixed at one end like this, and it is having a tapered cross section like this. Our bar is something looks like this, and let us consider its axis to be like this. Central axis. Consider this to be its central axis. I have to show it by a dashed line. Okay. Then this bar is subjected to some external loading, like it is subjected to an external pull which is given by force F. Let's assume this to be x-axis and this to be along y coordinates. Okay, this to be along y-axis. It is also subjected to one body force, what we call commonly as, or subjected to a force which varies along its length, like this, like this. Let's call this force to be equal to q of x. I am writing x because it's a function of the location where it is acting in the bar, inside the bar. This bar is of length L. This bar is of length L, and other thing is this, its area A. It's a function of x, as you people are clearly seeing that it's a function of length of the bar, area of cross section. Okay, length is constant. Then what else is there? Yeah, we have all the things which are there in the bar. So for this bar, let us consider very small element at some location, very infinitesimal element of length dx at some distance x from the fixed end. Okay, this is fixed O. Keep this in mind. Let us just zoom in this element or this element that I consider. Okay, let us see what's happening inside this element. So this element I am taking this So I'm taking very small element like dx. So this is not varying, like its thickness is so much small that it is tapering is negligible within this length dx. That's why I'm showing it with the uniform rectangle dx. It's of dx, and inside is a force acting q of x that I already told you. Okay, at the internal force that be acting on this, on the forces like this be acting this side, and this side be like this. Okay, because we have detached this element from the equilibrium body, or the body which was at equilibrium. So to keep this element, or while we were drawing the FBD of this small element in equilibrium, also we have to draw the other forces that will be coming as we are detaching it from some equilibrium system. So let from this side it will be f of x, and this side it will be increase a little bit, increase it because we are moving by a distance of d of x. So let that be f of x. There will be a small increase in the force, that will be d f of x, very small f x.
Danish,
Yes,
hello.
hello, yes,
Sir,
yes,
this bar is tapering, right? And is
yes.
section is a circular or rectangle taper bar?
Okay, right now we can assume it either to be circular, okay, for timing, because we don't have to do anything with the cross section right now, because I'm only deriving the mathematical formulation for it. So I will not be using anything, whether it's rectangular or circular. Let's for time being consider it to be circular, okay.
Okay. And sir, what is the meaning of Q of x? And Q of x is which parameter is represent?
Q of x, I told you, it is the internal body force that is acting on, distributed force that is acting on the bar also.
Internal force of
Eh,
body.
no, not internal force, is the external force, but it is a distributed force, which is a function of location on the bar. It is not constant, like it is like 10 kilonewton per meter here as well, and 10 kilonewton per meter here as well, but it's not constant. It will be something here and different at this end also. Okay, are you getting my point?
Okay. And sir, here you are, sorry, here left side you are writing f of x, and right hand side you are writing f of x plus df of x.
Yes, yes.
So it means this body is still equilibrium or
F of x is
move to right hand
it's
side.
axial force. Okay, because we detached it from some equilibrium system, so there will be axial forces acting on it. Okay,
Hmm.
we are seeing the equilibrium of this small element. So on the left side there will be only f of x, but as we move by a distance d of x, there will be some addition into the this actual force, that is we are denoting by df of x. Now we will see, if this part has to be in equilibrium, we will write the equilibrium conditions, what will be that. For that we just wait for that moment. Okay,
Okay. Okay, sir. Please continue,
okay,
sir.
okay. Actual forces we are denoting by f of x. Okay, then we will take the, for equilibrium of this, for equilibrium of this small element, what we will consider the summation of forces along x direction to be equal to 0. So it will be only in equilibrium when it will satisfy this condition. So taking this direction to be positive, we are having two forces. Okay, write those two forces, f of x plus df of x. Okay, then we have one more force acting in this direction, q of x. Okay, so it is acting per unit length, so total force will be q of x multiplied by d of x, q dx. Okay, then what else is the another force? It is f of x acting in the opposite direction, minus f of x. It is equal to 0. So when we will follow this thing, we will get df by dx is equal to minus q. Okay, that is the axial force within the bar is varying, and it is equal to the external uniformly distributed, not uniformly distributed, the distributed load that we applied on it. So in this formulation, let me write, I am not assuming this right now, okay? So then what we have to write? We have to write the axial stress, okay? We will write axial stress as, right, let axial stress will be again as a function of some function of the location. Then this axial force F of x will be given as that axial stress sigma of x multiplied by the area of cross section at that point, okay? So axial stress at any point inside the bar is equal, axial force at any point inside the bar is equal to axial stress multiplied by the area of the cross section at that point, okay? And how we can write the strain with the help of stress strain relationship, or this we can write this axial stress to be equal to E, we are considering E to be constant, okay, by Hooke's law, okay, constant, E times epsilon of x, where epsilon of x is strain, okay, and primarily it's axial strain only, because we are considering axial deformations only. And from your mechanics classes, you people will be well aware of the fact that strain is nothing but it is the gradient of displacement, that is du by dx, okay. Strain is this thing, okay. Then we can, what we can do is that we can do this f, we have this equation a, okay, substituting above things in equation a, okay, we have d by dx of f of x. F of x is but actually equal to sigma x times a of x. So sigma of x times a of x, okay, then what else is there, is equal to minus q, okay. Then what we, I can write in place of this sigma of x can be replaced by e times epsilon x, that will be d by dx of e times epsilon of x, a of x is equal to minus q, and this epsilon of x can be replaced by du by dx. I can write d by dx of e is con, e will be right there, so it will be e times a of x du by dx. Q, I will transport it to transpose it to left hand side, it will be plus is equal to 0. So this is the governing differential equation for the axial deformation of a bar, and where 0 is less than x less than L, okay. Now one more thing is that what are the boundary conditions on our bar is, if we see the boundary conditions, so the governing differential equation for axial deformation, formation of bar under external load, external load q of x is, we will copy this thing, okay. This is the governing differential equation with boundary conditions, with boundary conditions as, so our boundary conditions are, first is the displacement at the fixed end will be 0, u, u of x at x is equal to 0 is equal to 0. This is our first boundary condition, or we can directly write it as u of 0 or is equal to 0. Another boundary condition is that, yeah, I forgot that. For example, I should have noted this is their f. So q of x is varying like this. This q of x has a final value at like q of x at x is equal to l. That is the end of the bar. It is equal to f. Okay. So remember this. So another boundary condition we have force at end of the bar. That is, sorry, write it in black. So force at the end of the bar is EA into L, because A of x at should be area should be at the end of the bar. That is A of L, and displacement at the end of the bar du of L divided by dx is equal to the force applied F. Okay, keep this in mind. These are the two boundary conditions. So these two boundary conditions will be initially given to you to solve your governing differential equation or the bar problem. Your governing differential equation for the axial deformation of the bar, out of which these will be specified. Okay, specified, and these will be like one boundary condition among them is the essential boundary condition, another is natural boundary condition, or we call natural boundary condition also Neumann boundary condition, and the essential boundary condition or Dilcher boundary condition. I hope you people remember this. Okay. So now we have governing differential equation like this. For this governing differential equation, we will employ the same variational principle that I taught you in, I think, week third or week fourth. Same variational principle, and we have to calculate the functional of this governing differential equation, and then that functional we have to use our finite element method that I told you in last class, how to discretize our problem or discretize the domain, and then assume the elements. And with respect for each element, we have to assume some price solution, which will be function of some unknown constants, and those unknown constants we have to minimize our problem error in such a way that the error is our final solution is as close to exact solution as possible. So again, I will be repeating the same steps. Okay, steps that we require. So we can easily, I can write here, it can be easily shown that the equivalent variational form is equivalent variational form is as, so we can write its variational form as for bar problem we write the variational form like pi of u, because it's a function of displacement, pi of u as 0 to L, because our domain is from 0 to L, 1 by 2 e a du by dx का whole square, du by dx का whole square dx minus integral 0 to L q u dx minus f u at L. Okay, so let me give you a hint how we will be able to arrive at this expression is, we have to use the same variational calculus, like initially multiplying by our governing differential equation with the variation of u of x, then performing the integration on this d2u by dx square, okay, to reduce the order of the integration. Then we will be arriving at this expression and this expression. Okay, and this f u of L is obtained by incorporating the boundary conditions. Okay, If you repeat those steps, you will get this expression. Okay, I will write this expression as in an equivalent form like this. Let me take this expression from this side. This expression I will equivalently write this pi of u as pi of u to be equal to u, as this is an equivalent form, u minus we, where I will tell you what I am representing u by. U is equal to strain energy. Okay, strain energy. Why strain energy? Because its expression is equal to 0 to L 1 half of EA du by dx whole square dx. Okay, I hope you people remember it from strength of materials, that strain energy stored in a bar when it is deformed actually is given by 1 half of EA epsilon square, like this. It's the same strain energy and we are integrating it over whole bar length. Okay, then we have, and w, what is w of e? W of e we can write as work done by external forces. Okay,
Only.
hello, hello, are you able to hear me?
Yes, we are able to hear. I
Okay,
was just saying that W is the work done by the external load.
yes, external forces. Do you have any question?
No,
Okay, thank you. W is the work done by the external forces, and that work done is like this. This is the work done by the external forces. Look, Q is also the external force, and F is also the external force. And force multiplied by displacement is work done, and this is Q multiplied by dx over whole bar length 0 to L will be the force given, multiplied by displacement. Again, it's the work done. Work is force multiplied by displacement. So I will write this expression to be equal to 0 to L Q U dx minus, not minus, it's plus F U of L, because if I take this minus common from here, it will be minus times this plus this. So our this expression, let me highlight it with different colors. So this expression comes out to be, this is our work, external work done, and this expression comes out to be strain energy stored within the bar, strain energy u. Okay, I hope this thing is clear to you people. Now I told you how we have to deal with this problem, with this governing differential equation. We have to assume, we have to discretize our problem domain into smaller elements. Let for time being we will consider, once again, considering one element. Okay, and we will derive the element equation for that one element. Okay, so for example, let our element be like this. From this, I showed you this in the last class. This is at some coordinate x1, and this is x2, and this is varying here x. Let the nodal, these are, I already told you, these are nodes. Okay, nodal displacement at x1 is u1, and nodal displacement at x2 is u2, and nodal forces, let it be f2 here, and let it be f1 here. Okay, and let the length of this element be, let the length of this element be L. Okay, and there is already the distributed load Q acting on this element Q, and other things are same. And one more thing is, in above formulation I assumed A to be variable. So here I am assuming EA, that is the product of EA, to be constant. Okay, So this a here in the integration can we can remove this a ea to remain outside because it is constant now in our formulation. One more step we have to do is we what we have to do. One second, yeah. Now there are two nodal forces F1 and F2. Then our functional defined over this element. This is the functional equation. Now we have to define this functional equation over this element. So I will write the functional equation, functional defined over the element will be, you have to just look at the above equation. So the functional pi of u will be equal to, now look at the domain. Our domain is from x1 to x2, not from 0 to L. x1 to x2, you have to just replace the domain. And now it is 1 by 2 EA. You have u dash du by dx over whole square minus q u of x. Because I am combining these two integrals. D of x, and we have two forces F1 and F2. So it will be minus times F1 U1 minus F2 U2. This comes from this point, okay? Now we have a, it's not a problem here. Now for simplifying our things, we have to change the coordinate system of our element. The element that we assumed, we have to change its coordinate system. Like I will show you what we have to do. Copy. Sorry. We have to change its coordinate system like this. So this coordinate system is from it is from x1 to x2. We will change it to another coordinate system that is from -1 to limits 1, and it's known as s coordinates, okay? uh, so you will be questioning why we need to change it from -1 to 1. So here the limits can be anything. X1 can be varying from something 10 meter to 20 meter, or 10 centimeter to 20 centimeter, varying, and it will be very difficult when we do the integration. We put these integrals into our calculator and then we solve. But when this finite element, when we write a code for this elements or the bar elements, there they perform numerical integration. And for numerical integration, most of the numerical integrations, you must have seen that there the limits are from -1 to 1. So our motivation behind changing the limits or the changing the coordinate system is just to make the limits from -1 to 1, so that the numerical integration will be easy for integration purposes. So this is varying from -1 to 1, and this is s coordinates, okay? So how to change from x coordinate to s coordinate? So we will use interpolation. Like we have, what we have here, this is like this, this is like this. We have x1 here, we have -1 here, two values. We have x2 here, we have 1 here, okay? So and in between this is varying x here, okay? And in between this is varying s here. And we, if we use the interpolation here, we can get the expression for s to be equal to, like if I write s to be equal to, using interpolation, I will get the expression like this. You do this algebra at your place, it's very easy. X1 minus x2 divided by L, okay? And here x2 minus x1 is actually the length of element that I told you in last class. That L is coming here, okay? I will write using interpolation, okay? We can get this thing. Then s is like this. Solving it further, we will get ls to be equal to 2x minus x1. It is actually x1 plus x2. Wait a second. No, it's x1 minus x2. Okay, x1 minus x2, so that we will transpose these two, it's we will get 2x to be equal to ls plus x1 plus x2. Okay, we have to express our x coordinate system into s coordinate system now. X we will easily get, because we have to derive the value of dx, we need dx because it comes in our integrals. Ls plus x1 plus x2 divided by 2. I hope you people are following me. So that our differentiating from both sides is dx comes out to be ls. We have to differentiate it with respect to x, both sides. It will be x1 will be 0, x2 are constant 0, so it will be 1 by 2 lds. Sorry, it's lds. This is our first thing. Or we can write dx by ds. I have to write ds by dx. Sorry, ds by dx we can write to be equal 2 by l. Okay, from this, when we will be studying these uh, parametric, these higher order elements like quadrilateral elements or square elements, there we use this type of we call this as to be Jacobian, where we have to convert x coordinate system to s coordinate system. We will be studying that thing in the coming lectures. We got this point. Okay, then again we have to come to this point. Like in last class I told you, we can write one second. Okay, I told you in the last class that our solution, we express our solution u of x in terms of our shape functions and nodal values to be equal to n1 u1 plus n2 u2. Sorry, it's not bracket here. So in the matrix form, if I want to write it, I can write u of x to be equal to n1 n2 u1 u2. It's like this. Okay, where I define it n1 to be equal to x2 minus x divide by L, if you people remember it from the last class. And N2 I wrote to be equal to x minus x1, so x minus x1 divided by L. Okay, so putting the value of x here, we got x here. Okay, ls x1 plus x2 divided by 2. Okay, we will incorporate it x2 minus what we have to put, ls x1 plus x2, ls x1 plus x2 divided by 2 divided by L. If we solve it further, we will get 2x, we will get 2x 2 minus ls minus x1 minus x2 divided by L. If you solve it further, we will get a simplified expression like this: 1 minus s divided by 2 to be equal to n1. Okay, or you can confirm it by this, like we choose our s coordinate system to be equal to here like this we choose it to be minus 1, or x 1 and x2 was here to be 1 and s. Here x2 is equal to 1 and x1 is equal to minus 1. So putting x2 equal to 1 minus changing x to s divided by 2, n1 will be 1 minus s divided by 2. Similarly, n2, and if you solve this again, you will reach the same expression. N2 will be x, we have to replace this by s minus x1 is minus 1, minus minus is plus 1 divided by L. And one more thing, what is the length of the element in s coordinate system? It is 1 minus minus 1, it is equal to 2. That's why this 2 comes here, divided by 2. We have n1 and 2 equal to be equal to this. Our shape functions in s coordinate system to be 1 minus s divided by 2 and 1 plus s divided by 2. So our solution in u of s coordinate system, u of s comes out to be in matrix form 1 minus s by 2, 1 plus s by 2, uh, u1 u2, u1 u2. I am writing this to be equivalently equal to, where I will be representing it by matrices n. I am making it bold to represent it by the matrix n transpose d. Okay, where n transpose is given by 1 minus s by 2, 1 plus s by 2. Okay, this row matrix, and d is the vector. It's actually the vector of nodal coordinates, u1 u2, nodal value, sorry. Okay, this is the vector of shape function, and this is a vector of nodal, vector of unknown nodal values. Okay, so moving forward, we got our u of s to be equal to this. Okay, then u dash of s will be, if we differentiate the same expression, u dash of s, our u dash of s, if you follow the same equation, will be equal to du of x by dx, which will be equal to, because u of x is a function of x and s as well, so we have to differentiate it with respect u with respect to s, du by ds and ds by dx. Okay, okay, total integral. So if you will see du by ds, where we have written our du by ds. If you differentiate this du by ds here, if you differentiate it with respect to s, you will get this to be equal to u du by ds to be equal to minus 1 by 2, 1 by 2. Okay, u1 u2. Okay, this is like this. If you write the same expression here, you will reach at this expression 2 by l minus 1 by 2, 1 by 2. Okay, u1 u2. I am representing this thing by, this is again here, this is here again d, vector of unknown nodal values d, and I am representing this whole to be a vector denoted by b, and taking its transpose because it's a row vector here. Okay, one more thing is n1, differential of n1 is dn shape function by dx, it is equal, if I differentiate it with, it is minus 1 by l, if you see it carefully, and 2 dash will be equal to 1 by l. Okay, and one more thing is that I will have to differential of u dash whole square. So u is a vector here, so its square we can write as u dash transpose multiplied by u, if we consider it to be vector. Okay, so for example, if we had any vector a to be equal to 1 0 1 like this, we wrote na a square to be equal to this 1 0 1. Sorry, I will write, we write a square to be equal to
1 0 1, because it's vector multiplication multiplied by 1 0 1, only then it will be compatible. So this is actually here A transpose, this is actually A again here, that's why U square is A square, we can write as A transpose multiplied by A. So just refreshing your matrices concepts. Okay, U transpose U here. So put the value of U transpose here. What we have the value of U transpose? It will be U1, U2. Okay, U1, U2. Not it is U dash. It's U dash actually. U dash we got here. Okay, U dash here. You have to take its transpose. Okay. So there are two vectors actually here. This is BT transpose D. You have to take the whole transpose. Okay. First you have to take the whole transpose. It will be D transpose B transpose B transpose, or whole transpose will be B again. Okay, so again D is U1 U2, so its transpose will be D transpose will be U1 U2. So I'm writing U1 U2 here. Then I am writing when we will multiply it with U dash, this whole thing we will reach at this equation, 1 by L square 1 minus 1 minus 1 1, and again we will be u1 u2 u1 u2. This is a very simple algebra that I have skipped 3 4 steps here. You just do that algebra at your place. It's very simple. So we get u dash of whole square, or it is equivalently written as du by dx over whole square. Why I was computing this term? Because I need it here. I need it here actually. It is du by dx over whole square. Okay, so if I put all these things in this equation, pi of u, where it is pi of u, yeah, actually here, du by dx of whole square, equation B. If I substitute all these things in equation B, what will I write? This is C equation. Okay, substituting equation C and equation B, we will get our functional pi of u to be equal to, it's a very long expression I will write for you people. Since we changed our coordinate system to be, here it's x1 to x2, we changed it to -1 to 1. You have to write -1 to 1, -1 to 1. Then we have this term 1 by 2 u1 u2. Then we have ea by l square, ea by l square 1 minus 1 minus 1 1 u1 u2. We have l by 2 ds. Then we have another expression for q. Actually here it is, we have q times u of x. Okay, we have to put the value of u of x. Q, what is u of x? U of x is n1 u1 n2 u2. It is q1 minus s divided by 2 n1 1 1 plus s divided by 2 n2 u1 u2 u1 sorry, it's not divided, u1 divided by u2. And remember, we have to replace dx here. We have to replace dx here. Okay, dx is actually equal to l by 2 ds. Okay, write that ds, l by 2 ds. Then we have minus our boundary terms f1 u1 minus f2 u2. Okay, let me define one thing here. Let me define this to be equal to this integral. Okay, so like this is constant here, this is constant here, again u1 u2. So I will define one integral k. Let I call that term to be equal to k. K to be equal to minus 1 to 1 ea by l square. Ea by l square minus 1 1 minus 1 1 minus 1 minus 1 1 l by 2 ds. Okay, this integral to be equal to k. When I perform the integration, it will come out to be ea by l square, not ea by l square, ea by l 1 minus 1 minus 1 1. Okay, this is our k term. Okay, remember. Then the second term, this. Okay, here we have to remove only u1 u2. Let us denote it by denote without u1 and u2, denote this to be by k along with the integral. Okay, denote this by k, and this term q1 minus s1 plus s up to this point only, along with l by 2, along with this thing, l by 2 by r q term transpose rq of t, and this to be, and this by r beta transpose. Okay, r beta transpose. I will write for you for the simplification. So we are denoting in the above expression rq of t to be equal to minus 1 to 1, this integral minus 1 to 1 q times 1 minus s by 2 1 plus s by 2 l by 2 ds. Okay, so it is transpose. If I write rq, what is rq actually equal to? Rq will be actually a column vector. It will be minus 1 to 1 q 1 minus s by 2 l by 2 ds, and it will be minus 1 when I will be expanding it, q 1 plus s by 2 l by 2 ds. If you simplify this thing, you will get rq to be equal to ql by 2 ql by 2. Okay, it's very simple. Rq to be equal to this, q to be equal to this. So you have here f1 u1 minus f2 u2 here. Here we can write it as like this, no? F1 f2 in this vector multiplied by u1 u2. If we take minus to be common, minus times f1 f2. This f1 f2, I am representing this f1 f2 by r beta transpose. Okay, that's why now I clearly made you understand why I represented it by this. Okay, so r beta transpose, let me write it here. So r beta is equal to, or beta transpose is actually equal to f1 f2. It is nothing, nodal forces. So actual r beta will be equal to then a column vector of f1 f2. Very easy to follow for you. Okay, this thing. So if I put all these things, now I have c1 equation. No, we have c used, we have c used c. We have d1 equation, we have d2 equation, we have d3 equation. If we put all these d1 d2 d3 equations in our in here, here, let us call this to be alpha. Put d1 to d3 in alpha. our this functional term, that's pi of u. Pi of u simplifies to a very simple expression. It simplifies to this 1 by 2 u1 u2 k times our k matrix k times u1 u2 minus r q transpose u1 u2 minus r beta transpose u1 u2. Okay, I hope you people got this concept. Now we have to minimize this functional. Then for minimum of pi of u, it is differential with respect to the unknown nodal value should be equal to 0. That is dou pi of u by dou u1 should be equal to 0. If you differentiate this whole expression with respect to first with respect to u1, then with respect to u2, you will get these expressions. You will get 1 0, because with respect to 1 you it is, with respect to u1 it is 1 and it is 0. It is k times u1 u2 minus rq transpose 1 0 minus r beta transpose 1 0 is equal to 0. And another condition, dou pi of u with respect to u2, it again should be equal to 0. It comes out to be 0 1 times k k matrix u1 u2 u1 u2, then minus rq transpose we have 0 1 minus r beta transpose 0 1 is equal to 0. 1 second. So we got these equations. Okay, if we combine these equations in one equation in the form of a matrix, what we will get an equation like this. We'll get an equation like this: 1 0 0 1 times k matrix times u1 u2 u1 u2 minus 1 0 0 1 times r q transpose minus 1 0 0 1 or beta transpose to be equal to 0. Look, 1 0 0 1 1 0 0 1, this matrix and this matrix, just we can take common from everything. We can write our matrix equation to be equal to k u1 u2 minus rq transpose minus r beta transpose to be equal to 0. So the final element equation will be, if we put the values of this k, r q transpose and r beta transpose like this: k is this, r q is this, r beta is this. Our final equation will be equal to element equation EA by L 1 minus 1 minus 1 1 U1 U2 U1 U2. Taking this R beta and RQ and R beta to other side, I will get these to be equal to QL by 2 QL by 2 plus F1 F2. This is the final element equation. Okay, this is the final element equation. From this you can get strain to be equal strain. Strain, I told you epsilon is equal to du by dx, and your du by dx value is here. Here du by dx. Here, yeah, here it is. So it will be equal to 2 by L minus 1 by 2 1 by 2 u1 u2. Okay, you can write it as 1 by L u2 minus u1. Okay, and then stress sigma will be equal to E epsilon. It's easy. And your axial force will be equal to F will be equal to A sigma for this element. So you people are now well aware with the formulation how we got the element equation for our bar problem. This now the boundary condition will be varied or the load will be varied, but again we have to use always the same equation. And from this we will compute the displacement, nodal displacement u1 u2. From there we will compute the strains, and from that strain we will compute the stress, and from that stress we can get the axial force. Thank you everyone for joining this session. If you people have any questions you can ask. In the next session we will be solving the problems on this bar problem. 2 3 problems we will solve, and then we will move to 2D truss element, truss and then beam. That's very important. Thank you.
Danish, Mayuresh here. Can I ask one question?
Yeah, sure.
Yeah, Danish, regarding this, there was one question in the last assignment number 4.
Okay.
Yeah, this is regarding the choice of the shape function, and
Okay.
actually whether it is complied to the different loading conditions. Like
Okay.
there were cantilever beams with universally distributed load, then
Okay.
universally varying load,
Okay.
parabolic load.
Okay. Okay.
So just want to know, when we select the shape function with some polynomial, let us
Okay.
say second order equation, that is of
Okay.
order of 2. So
Okay.
how it will be complied with respect to the loading conditions?
So you are
Did you get
telling
my
that
question? Yeah.
how the shape functions are to be related with the loading conditions. Uh,
Yeah, I mean how, like whether such suppose I have one order of shape function, whether
okay.
will it be applicable for a load, like where the deflection is mentioned in terms, like exact solution is in terms of fourth order. Is it possible? So that only
So
how to
what
find
is
it, how to
important
load
is
it.
that if you look at the degree of the shape function,
Yeah,
so I will make you understand this concept by this thing. So there will be
yeah,
load has to do nothing with our, I mean to say that our problem. So load acts and it will be of different types. The main thing of our problem is the governing differential equation. What is the order
yeah,
of that governing differential equation that determines the type of the shape function that you use. Okay, for example, if there is a third order differential equation, there the third order of differential is existing. So for example, if I assume linear trial solution, if I assume linear trial solution and differentiate it thrice, then it will vanish at all. So I will be heavily left with nothing there. So you have to choose the order of this shape function or the order of the trial solution in such a way that it satisfies our governing differential equation. Are you
Is
getting
it
it?
possible for you to yeah, is it possible to explain with respect to the beam governing equation?
So beam governing equation are we are going to study in the next class. I will let you know in that class.
Okay, else otherwise with respect to bar equation.
Bar equation here we have.
Yeah, so with respect to this governing equation,
Yeah, we have
uh,
first first
yeah,
derivative existing here. Are you getting my
yeah,
point here? So in the first derivative, we assumed shear functions where I wrote it. Shear functions. One second. Shear functions we wrote. Shear functions here. X2 minus x1 divided by x2 minus x divided by l. So x is of order 1. Are you seeing
yeah,
here x is of order 1?
yes, yes,
So if I
yeah,
differentiate it once, so there will be something left for n1. Okay. So if this
yeah,
n1 was assumed to be constant, it will appear to be equal to 0. Okay. If I differentiate it, then my u
uh,
of x, that is u.
that means it is only one time differentiable, is it not? Shape
Yeah,
function.
yeah. One time it can be of higher order also. It can be of
Yeah,
higher order also. That's why I'm telling you it totally depends upon the order of the differential that is existing in our governing differential equation. Okay.
yeah.
So
Still, I'm
so
not getting actually means what I'm asking. No, mean this governing equation here in bar element is a single order, right?
yes,
One
single one.
order.
Yes.
So that means you need shape function also of the first order, is it
Yeah,
not?
minimum of first order.
Minimum of first order.
Minimum
Okay.
you can change you can take second order also. There is no prohibition in taking the second order also, but minimum you have to take at least first order shape function. Okay. That's why.
Yeah,
So
that because
I'm telling you, if you took it as constant, then if you differentiate it once, there will be nothing left. There will be 0.
yeah,
Same is the
right.
condition with beam equation. In beam equation, we get this derivative to be equal to d2 u by dx square. There we can use
Yeah,
quadratic shape functions. Okay.
yeah, yeah,
Yeah.
yeah.
In next class, I will be making you understand completely because next class,
Yes, yes, yes.
maybe not next session or next session after that one, because we have now truss elements, then beam element.
Right, Danish. Thank you.
Are you getting my point?
Yeah, thank you, Danish.
Okay. Thank you so much. If other people have any question, they can ask. Otherwise, they may leave.